Hello everyone, welcome back to this lecture series on engineering mechanics. In the previous lecture, we studied non-concurrent forces in plane and learned how such forces produces both translation as well as rotation. So we also solved numerical problems using direct moment calculation. So in today's lecture, we will extend that understanding by introducing an important principle called Varignon's theorem. So this theorem will help us to simplify the moment calculations, especially when several forces are acting at different points. So in this lecture, we will understand the statement and meaning of Varignon's theorem and how to apply it to numerical problems to determine the magnitude, direction and position of the resultant force. Now before moving to Varignon's theorem statement, so resultant also will have the three characteristics what a force will have. That is magnitude, direction as well as position. So once if you are solving the resultant by using the parallelogram law of forces, we can able to determine the magnitude as well as its direction. But the position is not possible to solve by using the parallelogram law of forces, as parallelogram law of forces is strictly restricted to concurrent force system. But in real-time structures, not all the systems being subjected to only concurrent forces. Many of the structures may be subjected to non-concurrent force system. So in that case, finding the position of the resultant also is a critical point to be considered. So hence this Varignon's theorem has been developed in addition to this parallelogram law of forces to find out the position of the resultant force. So let us first understand the theorem. So if a number of coplanar forces are acting simultaneously on a system, then the algebraic sum of moments of all the forces about any point is equal to the moment of the resultant force about the same point. So what this theorem tells us is very simple but very powerful. So instead of first finding the resultant force and then calculating its moment, we can directly calculate the moment of individual forces. We can add them algebraically and finally we can equate them to the moment of the resultant. So this approach will reduces the calculation effort as well as avoids any mistakes. Now look at the figure shown here. So in this case, six forces are acting on a body, all with different magnitudes, different directions, with different positions, F1 to F6. And their distance from their axis of the forces to a particular point, let it be considered as a O point, is being given as R1 to R6. So the question is something like we need to find not only the magnitude as well as the direction of the resultant, but also we need to find the position of the resultant, because all the forces are not concurrent. So in this case, we can apply the parallelogram law of forces, before which we will be applying the resolution of forces, finding the components of all these six forces along the x direction as well as y direction, then summing up all the forces in order to get two forces, one in the x direction and one in the y direction. Then we can apply the parallelogram law of forces to find out the magnitude as well as the direction of the resultant. So once the magnitude and the direction of the resultant is known, the final thing is that we need to find the position. So for which we are going to apply this Varignon's theorem. So what Varignon's theorem has mentioned is find the moment of all these individual forces about a common point. So here we are assuming that the point O is the common point. So we're going to find the moment of all the six forces about the point O. Let us start with O1. So O1 is acting right side above. So it will tend to create a clockwise moment about the point O. So that will be F1 into R1. Let it be negative because it create a clockwise moment. Next, F2 is acting towards left side. So it will try to create a anti-clockwise moment about the point O. So that value will be F2 into R2 will be positive. Then F3 will create a clockwise moment about the point O. The magnitude will be F3 into R3. Since it is a clockwise, the value should be negative. F4 will create an anti-clockwise moment. The value will be plus F4 into R4. And similarly, F5 will be F5 into R5, positive, clockwise both are positive. And F6 will create a clockwise moment about the point O. So that will be negative. So F6 into R6. So summing up all these things, you'll be getting the net moment acting about the point O. So already we calculated the resultant. the magnitude as well as the direction. So let me assume that the resultant is acting in this direction at a position R. We don't know the value of this R. So that is what is the question. We need to find the position of the resultant with respect to the same point O. So as per Varignon's theorem, so whatever we calculated, that is moment of all these individual forces about the point O, should be equated to the moment of this resultant also about the point O. That is nothing like R into the small r. That will create a anti-clockwise moment about the point O. So that should be positive. So once if you are equating these two, the left side components, everything is known, whereas coming on to the right side, the magnitude of the resultant has been already calculated by using the parallelogram law of forces. So hence, the small r is the only unknown. That is the position of the resultant. So using this only, the position of the resultant can be found out in addition to the magnitude as well as the direction by using the parallelogram law of forces. Now let us apply it in a problem. We have four forces, 10, 20, 30 and 40 Newton are respectively acting along the four sides of a square ABCD taken in order. We are supposed to calculate the magnitude, direction as well as the position of the resultant force, and they given the side of the square is 5 centimeter. So here all the forces are not acting in the same direction, which means that we need to find the components of all these forces about the x as well as y. Then we can use the reduced parallelogram law of forces equations to find out the magnitude as well as the direction of the resultant. Let us start with the x direction. So we have only two forces are acting in the x direction. One is 10 Newton and the other one is 30 Newton. But 10 Newton is acting in the right side, whereas 30 is acting towards left side. So 10 take it as a positive and 30 can be taken as a negative. So Fx will be 10 minus 30, which comes minus 20 Newton. Similarly, y direction we have 20 and 40. 20 is acting upwards, 40 is acting downwards. So Fi will be 20 minus 40 will be minus 20. Since both the forces, the components are getting it as a negative, so we'll get x-axis components will be left side and y components will be downwards. Let me assume this diagram like this. Then I need to find the magnitude of the resultant as well as the direction of the resultant. So applying that parallelogram law of forces equation, R is equal to root under Fx square plus Fy square, we'll be getting the resultant as 28.28 Newton. And for finding the direction of the resultant alpha, we'll be using the relation tan inverse of Fy by Fx. So which comes as 45 degree. So now we know this one. I'm assuming the direction of the resultant is going in this way. Since your Fx and Fy is acting like this, so obviously your resultant may be acting in the third quadrant. Right. So now we need to find the position of this resultant with respect to any one point, either A or B or C or D. In the problem, they didn't mention a specific point about which only you are supposed to find out the moment. So in that case, you can find the moment with respect to any point. So it's a simple suggestion is always try to have the reference point which is perpendicular to the axis of the resultant force. So here the axis of the resultant force is in this direction. So perpendicular to the axis of the resultant force, we have 2 points. One is the D and the other one is the B. So you can take any of these 2 points as the reference point for finding out the position. That will make the problem simplifier. Right. So let me assume the distance is D from the point B. So which means that I am assuming B as the reference point. So as per Varignon's theorem, I need to find the moment of all these individual forces about the point B. Then that has to be equated with the moment of the resultant force about the same point B. So let me start with the moment of the individual forces about the point B. So we'll start with the 10 Newton force. So here you can see 10 Newton forces acting at the point B itself. So since it is acting at that point itself, this 10 Newton force will not create any moment. Now going on with the 20 Newton force. So here the 20 Newton force is acting at a C even though, but the line of action you can see it is passing through the point B. So this 20 Newton force also will not create any moment about the point B. Let us move with the 30 Newton force. So here the 30 Newton force is acting at D and it is having the line of action is going in this way, which is not passing through the point B. So this 30 Newton force will create a moment about the point B. So taking B as a center and radius as this one B to D, rotating that force in the sense, it will tends to rotate in this direction. That is the anti-clockwise direction. So that will create an anti-clockwise movement. So that value will be positive. So this is the horizontal force. So horizontal force, if you want to find the moment, means that should be multiplied with the vertical distance. So vertical distance is AD. Since it is a square, all the sides will be of same value. That will be 5 centimeter itself. So it will be 30 into 5 centimeter. So that is 30 into 5, positive value. Now let us move with a 40 Newton force. So 40 Newton force is acting at A and the line of action is going in this direction. Which means that again this is also not passing through the point B. So this also will create moment about the point B. So since it is acting on the left side and it is acting in the downward direction, if I am rotating the force about the point B in the sense, it tends to rotate in this direction. That is again a anti-clockwise direction. So that will also create a positive value. So since this force is a vertical force, this has to be multiplied with the horizontal distance of 5 centimeter. So it will be 40 into 5. This is what is the moment of all the individual forces about the point B. Let me have that value. Right, so 10 into 0, 20 into 0, whereas 30 into 5 and 40 into 5. So we got the moment of all the individual forces about the point B. And this has to be equated with the moment of the resultant force about the point B. Now let us go with the resultant. So resultant is acting in this way, which the line of action is not passing through the point B. So obviously this also will create moment about the point B. So if I am rotating this force about the point B and the line of action is going in this way, so this will tends to rotate in this direction, which is nothing like a anti-clockwise direction. So that also will create a positive value. And already the magnitude of the resultant being calculated 28.28 and the perpendicular distance what we assumed is a small d. So we'll get the value as 28.28 into d. So equating the moment of the individual forces with the moment of the resultant forces about the point B, you'll get the value of the d. So d will be equal to 12.38 meter. Next, we shall move with one more additional example wherein not all the forces are straight forces, instead they are inclined forces, which means that we need to resolve all the forces. So we can see that 80 is inclined at a 30 degree with the horizontal. So resolving means we'll be having the vertical component and we'll have the horizontal component like this. Since the angle is given with respect to x-axis, so x component will be cos theta. So 80 cos theta. And y component will be 80 sin theta. Next, 40 Newton force making an inclination of 45 degree with the horizontal again. So horizontal component will have 40 cos 45 degree. And the vertical component will be going in this direction. So it will be 40 sin 45. Next, 30 Newton force makes an inclination of 30 degree with the horizontal. So horizontal component will be 80 cos 30 degree and vertical component will be 80 sin 30 degree. And finally, the 60 Newton force makes an inclination of 45 degree with the horizontal. So horizontal component will be 60 cos 45 and then vertical component will be 60 sin 45 degree. Now we got the components of all the forces about the x and y. So sum up all the x component 80 cos 30 minus 40 cos 45 minus 80 cos 30 plus 60 cos 45, you will be getting the x component of the resultant, that is 14.14 positive. Similarly, add all the y components of the forces 80 sin 30 positive plus 40 sin 45 minus 80 sin 30 minus 60 sin 45, you will be getting the y component of the resultant. So I can see that x component is positive, y component is negative, which means that the resultant will be going in this direction and your resultant force will be acting in the fourth quadrant. Right, so now finding out the resultant, will be applying the parallelogram law of forces. So R will be equal to root under fx square plus fy square. So substituting the values, you'll be getting the R value as 20 Newton and going on with the alpha, you'll be having the relationship tan inverse of fy by fx will comes as 45 degree. And we are assuming the position we are going to find. You can see that the resultant is going in this way. So we are assuming the point A or point C to be the reference point about which only you are going to find the position. So let me assume the A point as the reference point. the distance is assumed as d from the axis of the resultant about the point A. So that is what we need to find it out. Now we need to apply the Varignon's theorem. So already we found out the vertical and the horizontal component of the forces get the moment about the point A. Let us start with the 80 Newton force. So here you can see that 80 Newton forces acting at A itself. So this one will not create any moment. Now let us move with the 40 Newton force. So vertical component will be acting in this way, horizontal will be acting in this way. So vertical component, you can see it is passing through the point A. So this vertical component will not create any moment about the point A. Whereas horizontal component, if I'm rotating, means it will tends to rotate in this direction, anti-clockwise direction. So that value will be 40 cos 45 into perpendicular distance is 2 meter. So positive anti-clockwise movement, so it should be positive. Now let us move with the 80 Newton force. So 80 Newton vertical component will be like this, horizontal component will be like this. So vertical component line of action is passing through in this way, which is not passing through the point A. So hence it will create a moment. So rotating this force about the point A, it will tends to rotate in the anti-clockwise direction. So that value will be positive. So the value will be 80 sine 30 into horizontal distance, which is 1.5 meter. Now let us move with the horizontal component. So a horizontal component also, the line of action is going in this way. It is not passing through the point A. So rotating this force about the point A, it tends to rotate in the clockwise direction. So that value will be negative. So minus 80 cos 30 into the perpendicular distance is a vertical distance. So into 2. Let's move with the final thing, that is 60 Newton force. So horizontal component is acting in this direction, vertical component is acting in this direction. Now you can see the horizontal component is passing through the point A. So that will not create any moment, whereas the vertical component will have a moment about the point B, which is in the clockwise direction. So that value will be minus 60 sine 45 into horizontal distance. Since the force is a vertical force, multiply with the horizontal distance, that will be 1.5. So that's what would have been shown here. So 80 is that one, 80 cos 30 into 2, then 80 sine 30 into 1.5, 40 cos 45 into 2 positive, minus 60 sine 45 into 1.5. So that is what is the moment of all the individual forces about the point A. And this has to be equated to the moment of the resultant about the same point A. So taking the moment of the resultant about the point A, so resultant is acting in this direction, line of action is going in this way. So if I am rotating the resultant with respect to the point A, it tends to rotate in the clockwise direction. So that value also be negative. So minus R into D. Since R has been already calculated, this can be found out by using this one. So minus 20 into D. So equating this one with this one, we'll be getting the distance. So D is equal to 4.28 meter. So that is here, I can write it here. So minus 85.64 will be equal to minus 20 into D. So equating these two, we'll be getting the value of D. Now let us go with an application point of view. A man and a boy carry a weight of 300 Newton between them by means of a uniform pole 2 meter long and weighing 100 Newton. Question is, where must be the weight be placed so that the man may bear twice as much of the weight as that of the boy? So this is what is the question. So here they gave the pole is 2 meter. So the weight of the pole is also been given as 100 Newton. So since the pole is having its own CG, so about that point only the weight will be acting. That is at 1 meter distance, the pole will be, the weight of the pole will be acting 100 Newton. So since it is a gravity, so it is acting in the downward direction. Next, we have the man and the boy being placed somewhere. Right. So question is, where must be the weight to be placed there? So what is that weight is? 300 Newton. Where should be placed so that the man may bear twice as much of the weight so as that of the boy. So in that case, we need to place this 300 Newton weight near to the man, so that only this man may be carrying somewhat a higher weight comparing to the boy. So I'm assuming that the weight being placed somewhere here near to the man. So let the distances be x from the man, so that the distance from the boy will be total is 2 meters. So 2 minus x will be the weight. And here they mention that the man should carry twice the weight than comparing to the boy. So if boy is carrying a weight of W in the sense, the man should carry a weight of 2W. Now applying the equilibrium equation, since the pole should be in equilibrium condition, the vertical forces summation should be equal to 0. So in that case, we'll be having W plus 2W both are acting in the upward direction, whereas the weights 300 Newton and 100 Newton are acting in the downward direction. Putting those things in the negative, we'll get the value of W. So W will be 133.33 Newton. So now the boy will carry a weight of 133.33, whereas the man will carry the weight of 266.67 Newton. So, but that is not the question. The question is where that 300 Newton load should be placed. So in that case, we can use the moment condition. So we are taking the point A as the reference. We are going to take the moment of all the individual forces about the point A. Right. So if I am taking this one, moment of all the individual forces about A and equating it to 0 because it is in equilibrium. So equating to 0, you will get the value of this x. Let us start with the this W. If I am taking moment about the point A, let us start with the force W. So since the force is acting at a point A itself, this will not create any moment about the point A. Now going on with the 100 Newton force, so this will create a moment about the point A. If I'm rotating this force about the point A, it will tends to rotate in the clockwise direction. So that value will be negative. So distance perpendicular to sense is 1 meter. So the moment will be minus 100 into 1. Now let us move with the this 2W. So 2W also will create moment about the point A. If I'm rotating about the point A in the sense, this tends to rotate in the anti-clockwise direction. So that will be a positive value. So the value will be 2W into the total distance about the point A. Horizontal distance is 2 meter. Okay, W has been already calculated. You can substitute that value. Now moving on with the 300 Newton force. 300 Newton force is acting downward direction. So if I'm rotating the force about the point A, it tends to rotate in this direction. There is a clockwise direction. So that will create a negative moment. So the value of that moment will be minus 300 into the horizontal distance between the line of action of the force and the point A. That is nothing like 2 minus Ex. So that is what to be written here. So minus 300 into 2 minus x plus 2w into 2 minus 100 into 1, which will be equal to 0. So solving this one, you can get the value of Ex. So x is 0.55 meter. So to summarize today's lecture, so Varignon's theorem will simplify the moment calculations. The resultant moments will be equated to the sum of the individual moments, and the theorem is extremely useful in non-concurrent force systems. And in the next lecture, we'll continue with the applications of non-concurrent forces and couples. Thank you.